Hello and welcome to our lecture 7, where we're going to look deeper into the tincan module, which is responsible for implementing the data path for the typical packet handling in IPOP. So tincan is the module that's responsible for setting up links, the tincan links that are the tunnels connecting our VPNs or endpoints in a P2P manner, and for handling packets that are coming into and out of the virtual network. So these are private links. They can be encrypted and they can be authenticated using techniques that are based on public key cryptography. In particular, typically, IPOP uses the UDP transport and the datagram transport layer security, or DTLS, for encryption and authentication. IPOP-tincan is also responsible for handling net traversal, and that, as we'll see, includes the ability to determine a reflection, use a reflection service to determine an endpoint at the edge of the net, and also, when net traversal fails, use a relay service through the turn protocol. So here's a refresh of the tincan architecture that was described last time, and we're going to start zooming in into the lower module here, which is the tincan and the IPOP tab. So as I mentioned in the previous lecture, the low-level interface to the OS virtual network device is handled by the code that deals with reading and writing from the STAP device and buffering this data and eventually passing that along to a packet handling thread in tincan. So the low-level code here has really not a lot of functionality other than being able to talk to the TAP device for different operating systems, buffer things, and call the appropriate function up in tincan. So most of the interesting stuff happens in tincan once a packet comes in. So now a packet is in tincan and it's being handled. So the packet will have a destination IP address. This application is sending, let's say, a TCP packet to a web server on the other side of the IPOP network. So the destination IP address will tell in tincan which link to use, which tunnel to send this message through. So tincan will keep a mapping. What is the virtual IP address and what tincan link does it map to? Most of the time, if communication has already taken place between two peers, there's already a link that exists between them. But sometimes a link will not exist. So looking up, based on the virtual IP address, is there a link that exists? If that lookup is successful, then this packet is going to be delivered to the libjingle library to send it over the physical network interface and tunnel through the other side of the network. It's possible that there's no virtual IP address link associated with a virtual IP address. If that's the case, tincan doesn't know how to handle it, and he essentially sends it up, throws it over the fence, so to speak, to the controller using the tincan API, which we'll see in the next lecture. So basically, a packet typically will go this way and out through the physical network tunneled. And if the packet, tincan doesn't know what to do with the packet, the path would be up to the controller, and the controller will handle that event. For example, the controller may handle an event by determining, oh, this is an IP address of a node that I know of, but we just don't have a link created with that node. So what the controller will do in that case is use the API to call tincan to set up a new link. Now, setting up a new link involves a few interactions. The first will be to discover what is the link, the destination of this link on the other side of the network, and to message that destination that, hey, I want to create a new tincan link with you. That's done through the peer discovery notification that's implemented by the OSN server using the XMPP protocol. So assuming that a link is created, then the IP address for that link is mapped into a table that's maintained in tincan, and then any further packets that come in for that virtual IP address will take the quick path that goes, as in the previous slide, goes from TAP to packet handling out through the physical network. So let's take a deeper look into how a link is established. So the link setup begins by using the XMPP service to tell the other peer that a link is requested. So let's say that this is Alice, and Alice got a message with a virtual IP address that maps to Bob, but there's no link with Bob yet. So the first thing that Alice is going to do is use the XMPP service to tell Bob, or ask the XMPP server to deliver a message to Bob that says, I'm Alice, I want to connect with you. And it will also tell Bob what are all the endpoints that Bob should try to use to connect to Alice in the physical network. So these are pairs of IP ports and protocols that Bob will be attempting to use to create a P2P tunnel. This also carries a fingerprint of the X509 certificate, public certificate of Alice. And this is going to be used when Bob and Alice try to negotiate a link. They're going to exchange certificates, and the fingerprint will allow Alice and Bob to determine that they are really who they're claiming to be. So XMPP is used to send this relatively small message with this information, the endpoints, the intent to connect, and the fingerprint. But to determine the endpoints, first of all, Alice needs to learn what addresses is she listening on. And this could be a local address in the computer that she's running, but if she's behind the net, she will also have an address on the edge of the net. The stun protocol will allow Alice to discover what address the public network sees from Alice. So Alice will send a message to the stun server and say, what do you see my request coming from? And the stun server will tell, oh, I see you're connecting from IP and port endpoints such as this. And Alice will discover that information about her net mapped endpoints and will store that and keep that information so that anytime she wants to connect to somebody else like Bob, she's going to send that information along the request message. The way net traversal works, and this is again handled by the libjingle library, the way it works most of the time with the help of this stun service. And the stun service, there are plenty of public stun services that can be used. They essentially tell just what UDP endpoint a message is coming from in the payload of a reply message. So for most nets, the nets that are so-called cone nets, the way a peer-to-peer tunnel is going to be established is Alice requests from the stun service what is her endpoint, and Bob does the same thing, and they exchange these endpoints, and then they're going to start sending messages to the endpoints that they learned about. And for a cone net, it turns out that the same endpoint that was used for the stun server can be used, let's say, by Bob to try to communicate back with Alice. As long as Alice and Bob are simultaneously sending messages on these endpoints, and as long as you're using a cone net, it may take a few iterations, but eventually they're able to create a tunnel in a P2P manner that punches through the net. That's called hole punching through the net. A large percentage of nets in the internet work in this way, and for the most part, P2P connections are established in this fashion. Now some nets, a fraction of nets, the so-called symmetric nets, do not work in this way. Basically, if you request the stun server to tell you what endpoint you're coming from, and then you tell another node, here's the endpoint you should try, the symmetric net will create a different mapping for the other endpoint and will not allow for this hole punching to work. So in that case, we're essentially out of luck unless we try to predict ports in the net, which is difficult and not reliable. An alternative is if you have a node on the public internet that can work as a relay, then you can use that relay node to communicate between Alice and Bob. So instead of having a P2P link between Alice and Bob that punches holes through the net, you're going to ask a third node like Carol on the public network that is a turn service to be able to relay all messages from Alice to Bob. So the turn service will allow Alice to ask for an endpoint for her to tell Bob to use. And now this endpoint is going to be off the relay, of Carol in this example. And Alice and Bob both will be using endpoints of this public relay to communicate with each other. All of this complexity is, again, abstracted from the application. The application will not know that XMPP service is being used, will not know whether stern or turn is being used for communication. This is all abstracted and presented at the end of the day as a virtual IP link that's carried over a tin can tunnel.